Okay, this will be the lecture for Chapter 7, and it'll be talking about energy, and just kind of something to pay attention to is energy is really important. I'll be talking about energy pretty much for a lot of the rest of Physics 101, and we'll talk about energy more and more in Physics 102. I really care about essentially where the energy is. So we're actually going to start off by talking a little bit about work, and yeah, I know work sucks. But work is kind of the transfer of energy, so we'll talk about work, we'll talk about energy, and there's two flavors of energy. We're going to talk about potential and kinetic for now. We'll say that energy is going to be a conserved quantity, and I'll kind of relate work and energy together. We'll talk throughout this lecture about machines, and we'll kind of finish off with power, which is essentially going to be how fast you do work. So as we kind of move our way to start talking about work, let's just start with some thoughts about a ramp. You know, if you take a look at these two ramps right here, ramp 1 and ramp 2, well, you know, ramps do seem to make lifting things easier, right? That's why the back of the U-Hauls all have, you know, the ramp on them. Some thoughts is, you know, the slope is going to matter. I mean, if you think about it, this guy right here is, you know, pushing pretty hard, and this guy right here is not pushing so hard. So steeper is harder, and it does seem like you get something for nothing. I mean, if you push this thing all the way up the ramp, it seems like, you know, like this guy right here, he got, you know, more of a free lunch, if you will, than this guy did. But it turns out that there is no such thing as a free lunch. So I want to talk a little bit about the forces that it takes to push a ball up a ramp, but before we do that, let's kind of talk about just having a ball on a table for a little bit. A table can't ever push anything but perpendicular to it, so a table that is supporting this ball can only push straight up. I mean, it would be kind of silly if I, you know, set a ball down on a table and it shot off to the side, right? The only way it would shoot off to the side is if it had a force on it in this direction right there, and we know that a table can't push in that direction right there. So this ball is not accelerating. It's got two forces on it. It's got its weight, mass times gravity, and it's got this support force. And again, we're never going to have a support force that is not perpendicular to the surface. Now, kind of the implication of this is what's going to happen if I, you know, went ahead and put a ball on a ramp. So I went ahead and did this guy right here. Well, again, this ramp can't push in that direction, and it can't push in that direction. The only place that ramp can push is going to be in this direction right there. So that's not going to happen, and that's not going to happen. So let's talk about the forces involved for lifting the ball straight up. I mean, this ball right here is going to have some weight, its mass multiplied by gravity. And if this man were to lift this ball right up here, then he has to apply a fairly large force. One thing to kind of keep in mind is the distance that he has to apply that force is actually going to be quite small. Now let's take a look at the amount of force that's needed to lift this using the ramp. Now we know that the ramp can only push in that direction right here, and this ball still does have its good old mass times gravity in that direction right there. And, you know, don't pay too much attention to, you know, some of the angles and stuff right here, but suppose I wanted to break these guys up into components, and it would kind of make sense to break this force up into two components. It's going to be a force in that direction, and there's going to be a force in this direction. So kind of what I've done is I've broken this blue arrow up into these two red arrows, and what we can kind of say is this man's going to push it up at a constant speed. So that arrow right there is going to roughly cancel out, or is going to exactly cancel out with that arrow right there. And so the ramp is supporting most of the weight. So this man right here, he only has to apply this tiny little force. So it is true, you do need to use less force to lift a boulder via the ramp. Now the question is there such thing as a free lunch? And the answer is no. And kind of the key to it all is going to be this distance that he has to apply the force over. This is a much larger distance than on the previous slide. So kind of the question is which man does more work? And the answer to that is it's going to be the same. So if kind of the basic definition of work is going to be equal to a force multiplied by a distance, and kind of the units for that, it could be a Newton times a meter, and that's a special type of unit. We're actually going to call this unit a joule. So when we talk about how many joules something is, we're talking about how much work was done. Now, take a look at this guy right here. Small force over a large distance, large force over a relatively small distance. So the amount of work that was done is going to be the same for both men. So kind of the way that this works itself out is work is going to be equal to a force multiplied by a distance. Here we've got a small force, so the force is relatively small over a large distance, right? We have to push it this big entire way. This guy right here has to support a large force over a relatively small distance, right? Just this distance right there, and it turns out that they balance each other out perfectly. So the amount of work done is going to be the same for both men. Now, ramps are actually machines, and something that machines do is they give us something called a mechanical advantage. And essentially, mechanical advantage allows us to play games with force and distance. Essentially, we're diluting the force over a longer distance when we use a ramp, but again, for all machines, the amount of work you do is going to always be the same whether you used the machine or whether you didn't. Other examples might be something like levers or pulleys, and we'll talk about those in a little bit. Now, what machines do is they're just going to allow us to multiply forces or change the direction of forces, but one thing that they can't do is they can't multiply work or this thing called energy. So it doesn't allow us essentially a free lunch. Now, kind of the basic principle of a machine is you're going to have some input and output. And essentially, the work in has got to be equal to the work out. Remembering, of course, that work is equal to force multiplied by distance. So what this says is the force in times the distance in must be equal to the force out times the distance out. And you can kind of see that as the distance out goes up, then the force on the output side can go down, much like we saw with the ramps. So let's just kind of think about a lever. Suppose I wanted to lift this rock right here. Well, yeah, sure, I could grab it with my hands and try to lift it, but I do need a lot of force. So what if I were to kind of put a bar under it and put a pivot right there? I do need a relatively large force to lift this guy, but now over here I can apply a relatively small force. One thing to kind of keep in mind though is I have to apply that force over that big long distance, this big long distance right here. So here the distance is large, the force is small. Now how far can I lift this rock? Well, it turns out that I can't actually lift this rock too awful far because it's kind of close to the pivot point. So the distance is small and the force is up. So what we're kind of saying is the work is going to be the same on both sides. And kind of see that down here. Distance is large, force is small. Force is large, distance is small. You can also kind of see this in pulleys. I mean, if you had a pulley that was like this and you had a rope around it and you were trying to lift a rock, well, that's actually not too awful useful. Why? Because, well, as you pull up right here, or pull this guy down, and you're essentially pulling this guy up. But if you were to turn this guy around and put it like this, then you can kind of see this girl is applying a force, but she gets more bang for her buck because there's also going to be a force right here. So we have two forces, so what comes out is going to be twice as much as what she puts in. However, the caveat is that she's going to need to pull about twice as much rope as she would in this case right here. So right over here she's going to have to pull twice as much as she does right there. And you've probably seen this if you've ever seen anyone pull an engine out of a car. What they do is they hook up a whole bunch of these guys and they pull out like 20 feet of chain to lift the engine up, maybe a couple of feet. And kind of what's going on is they don't have to apply a lot of force. One person can lift the engine out, but they have to apply it over a very long distance. So give yourself a minute or so and think about lifting a barbell, and how much work would you do if you made that barbell twice as heavy and you lifted it the same distance. Well, work is going to be equal to force multiplied by distance, and if we made the barbell twice as heavy, then this guy has gone up by a factor of 2. This guy has kind of remained the same. We're lifting at the same distance, so I would expect the work done to be twice as much. So what happens if you do work to something? Well, it turns out that you're actually going to be giving it this thing called energy, which is going to essentially be a potential to do work. So if you've done work to something, then it has gained some energy, and once it has energy, then it can do work. So work and energy are kind of actually related. Work is going to be the flow of energy, and kind of not surprisingly, energy is going to have the same units as work. It's going to have a unit of a joule. So we can kind of think of work being a change in energy, if you will. Now, we're going to talk about two types of energy. We're going to talk about kinetic energy, which is going to be the energy when something is moving, and potential energy, which is essentially going to be stored energy, and it could be stored in any number of places. It could be stored in height, right? If I had a rock and I lifted it up to the top of a building, then now it's going to have what we would call gravitational potential energy. Other types of potential energy could be energy stored in springs. I mean, if you take a rubber band like that and you go ahead and you stretch it out between two fingers, then it has the potential to do something. It can be shot across the room. So stored energy is just kind of held in readiness, and it's just waiting to do some work. So examples, stretch bow or a stretch rubber band. Potential energy is going to be gravitational potential energy, right? This rock can do something. It can fall down and it can get moving, and once it's moving, it has this kinetic energy. So let's talk about the energy associated with height first. So this is going to be gravitational potential energy, and again, energy stored in height. And kind of the simplest possible thing is suppose you have a rock and you want to do some work to it, so you're going to have to apply some force, and you're going to have to apply it over some distance, and this is going to kind of be the height. So we go ahead and we lift this rock up, and we put it just right there. Then the amount of work that you had to do is going to be the force multiplied by the distance, and the force is actually going to be equal to the mass multiplied by gravity. Why? Because the force has got to be equal to the weight that you're overcoming, and the distance is simply going to be the height, so mass times gravity times height, and occasionally we kind of just abbreviate this. PE, potential energy, is equal to mass times gravity times height. So kind of what happened is all the work that you did went into energy, and it went into potential energy. So let's just kind of think about this coming back to a ramp. This guy right here moves the rock right here. This guy right here moves that rock up right there. And as long as these heights are the same, then the amount of energy, the mass times gravity times height, are the same. Therefore, the amount of work that was done has got to be the same. So you can kind of see that it's all related, same. So let's just work an example problem. So here we have just a standard Wendy's medium bacon eater combo, and it's got 1650 calories, which is also a unit of energy. Turns out that this is about 6.9 times 10 to the 6th joules. Yes, that is a huge number. And if we could theoretically convert all of this energy into height, how high could you climb if you weighed about $1.50, which is 69 kilograms? So kind of what we're going to do is we're going to say that all of this energy is going to go into potential energy, which is going to be equal to mass times gravity times height, and kind of what we're looking for is how high can you go. So what we can do is we can say, well, we're going to divide this side by mass and gravity. If we do that, we have to divide this side by mass and gravity, and these guys are going to cancel out, so the height is simply going to be equal to the potential energy available to you divided by mass and gravity. So 6.9 times 10 to the 6 divided by your mass, 69 kilograms, and gravity, which is going to be 10. and it comes out to be a height of about 10,000 meters, which is actually higher than Mount Everest. Now, the reason I said theoretically is because we can't convert all of this energy to height. Some of it does go into your basal metabolism, so keeping your body warm, keeping your organs running, and stuff like that. So let's just wrap up this half of the lecture by taking a look at some more numerical examples. We're looking for how much work is done to lift a 10 kilogram rock to the height of 1 meter. So here we're going to have my 10 kilogram rock, and we're going to lift it up a distance of 1 meter. And what we kind of have to do is the force we have to apply is going to be equal to the weight, which is going to be mass times gravity. That's the force that we're going to apply. So we're going to say work is equal to force multiplied by distance, which is going to be mass times gravity times the distance that you lifted up. So that's going to be 10 kilograms multiplied by gravity, which is 10, and then the distance is 1, so the amount of work that you do is going to be 100 joules. Now, if instead you decided that you're going to push this rock up a 2-meter long ramp, so now it kind of looks like this, then how much force are you going to need? Well, you already know the work that it took, and now you're going to say work is equal to force times distance, and this is now what we're looking for. The distance is 2, so we're going to say 100 joules is going to be equal to the force times 2, so the force would be 50 newtons. Keep in mind that the force right over here would be 100 newtons. Now, how much potential energy would that rock have if we lifted it to a height of 1 meter? Well, the work that you've done is going to be equal to the potential energy, and you can convince yourself of that. So it's going to be 100 joules is going to be the potential energy. And if we were to double the height, then how does the potential energy change? Then it's going to be 2 times as much, or 200 joules.